Okie dokie, march we onward. This is lesson 12. Nope, I'm wrong. This is lesson 13. It's the chain rule. Lesson 13, it's the chain rule. This is another one of those big moments in our course. This is one of those things that if we don't get right, it just keeps coming back. For all the Whovians listening, this is the Dalek of our course. If we get this right, we're okay. If not, it keeps recurring and it comes back to haunt us. The chain rule helps us take derivatives of functions like this. See, so far we know how to take derivatives of polynomials, and if we were to expand the brackets on this thing, we could take the derivative of that one term at a time. But that involves the binomial expansion theorem, and my experience is you don't remember that. And even if you did remember that, this is just way too complicated. So the way I'm thinking about this function is really a chicken nugget to the 8th power. And of course we know that chicken nugget is x squared plus 1. And there are two things that we know. We know how to take the derivative of chicken nugget to the 8th power. That's not hard. And we know how to take the derivative of x squared plus 1. That's not hard. So if you're one of those people that does a lot of mathy talk, this is function composition. This is a function of a function. One function has been substituted into another. The chain rule helps us take derivatives of composite functions. And it does that in the following way. This is right out of the OpenStax book. This is Strang's writing. So we're going to let f and g be functions for all x in the domain of g, for which g is differentiable at x. It just means that g prime has to exist. And f is differentiable at g of x. It just means that this has to exist. Then the derivative of this composite function is given by f prime at g of x times g prime of x. There is a nifty way to explain this in your textbook on pages 295 and 296. There's a proof for why this works. I will not go through that in the video, but there is a proof for why this works. We take the derivative of the outside function, evaluate it at the inside function, and then the derivative of the inside function. They get multiplied together. This is not a multiplication. This is the only multiplication. If you're using Leibniz's notation, dy dx is dy du times du dx, and I'll explain that as we go along. I've also included in this capture, there's an animation that helps you to see the chain rule in action. That animation is worth clicking on. Even in the PDF version of the book, you can click on the animation and it opens up a web page in a browser. So there's a bit of a strategy that Strang offers. You have to begin by identifying the outside function and the inside function. This is the outside function, and this is the inside function. And then we take the derivative of the outside function, evaluate it at the inside function, take the derivative of the inside function, and then write it down. This is a situation where our functions have layers. Ogres have layers, onions have layers. This function has layers. The outermost layer, the f of x, is the function that raises things to the 8th power. It is the chicken nugget function. It is the function that raises things to the 8th power. The inside function is the thing that gets substituted in there to make this, and that's x squared plus 1. So just confirming, f of g of x is what you get when you take this and stick it in there. So what does the chain rule say? The chain rule says that the derivative is f prime at g of x times g prime of x. So the g prime of x part, that's easy. The f prime at g of x part, that's a little harder. So the derivative of f is 8x to the 7th. So f prime at g of x is what happens when we take this and put it there. 8 times x squared plus 1 to the 7th power. That's what the chain rule says is the derivative of that function. So we take f prime at g times g prime. So you've got this in your notes. You've got this in your notes. I'm going to go one more. Find dy dx if y is the sine of x squared minus 4. So we ask ourselves, what's the outside function? What's the inside function? How do I know what the outside function is? Well, I think to myself, if I were to substitute an x value into here, this would be the first place we plug that x. That is likely the inside function. And then we'd take that answer and take the sine of that answer. The sine function is the outside function. And you can confirm that if you put g in there, you get this back, and that's what you wanted. So we ask ourselves what f prime is. The derivative of the sine function is the cosine function. And so dy dx is f prime at g of x times g prime of x. F prime of g of x. So we take this and put it in there times g prime of x. And we're done. Outside function, derivative, evaluated at inside function times inside function's derivative. We peel away the layers one at a time. If you're going Leibniz's way, and I'll just add this as a side note here. That's a side note. If you're going Leibniz's way, Leibniz would take a look at this and say, well, why the outside function is the sine function. So he would say that this is the sine of u. I call it chicken nugget in my classroom, and probably now also on the interwebs, but traditionally mathematicians call this u, where u is x squared minus 4. And Leibniz would say, well, the derivative of y with respect to u is the cosine of u, and the derivative of u with respect to x is 2x. Just taking a derivative, taking a derivative. So when I want dy dx, well, I just take dy du and multiply by du dx. That's the cosine of u, but we don't want to write u. We want to write down what u is. What you are? No, what u is. Dy du is the cosine of u times du dx. It's the same process. This just shows us a different way to decompose the function at hand. That notation is somewhat useful when there are layers upon layers upon layers. Find dy dx if y is the square root of sine squared x plus 4. Sine squared x plus 4. How do we find dy dx? Well, I'll go Leibniz on us for a moment. The outermost function, this is the outermost layer. The outermost layer, the last thing we do if we're evaluating this function is we take a square root. That's u to the 1/2 power. And then what's the u? Well, u is something squared plus 4. Something squared plus 4. Well, what's the thing that gets squared? The innermost function is sine x. If we were substituting an x value in, we would figure out its sign first, then square that answer and add 4, and then take the square root. So we take the derivative of y with respect to u, power comes down in front, exponent decreases by 1. We would take the derivative of this polynomial, no trouble, and we would take the derivative of the sine function. We've got that. So when we want dy dx, we string these together. 1/2 u to the negative 1/2. Well, what's u? U is v squared plus 4. But what's v? Sine of x. Times du dv, well, that's 2v, but what was v? V was sine x, and then dv dx. Maybe you cancel the 1/2 and the 2, that probably makes sense to do, but there's no real reason to simplify beyond that. There are things that you should be able to do at this point. There are things that I commend to you. I'm going to ask you to differentiate. One of the functions will be 4 minus 3x to the 9th, and the other one will be the cosine to the 4th of 3t squared plus 1. We'll see. This is fairly straightforward. This is a little bit more complicated. One more thing before we go. We're going to let f and g be differentiable such that, and we're going to have this like table, and there are 3 different x values, and I'm going to give you information about f and g and f prime and g prime, and I'm going to put a whole bunch of numbers up here, and most of them you won't need, and boy is that going to frustrate you. I want to find h prime at 2 where h of x is f of g of x. Well, how does this go? Well, h prime at 2 is f prime at g of 2 times g prime of 2. This is just the slide we had at the beginning. H prime is f prime at g times g prime. So now it's almost worth pausing the video here and seeing if you can identify what g of 2 is, what f prime of that is, and what g prime of 2 is. It's almost worth doing that. Almost. I'll pause. I hope you did it. G of 2, that's 3. So we want f prime of 3 times g prime of 2. Well, f prime at 3, that's -5, and g prime at 2, that's -2, and there's your answer. You have got to be comfortable doing questions like that, because stuff like that is going to pop up. All right, I'm set if you are. We'll see you in class. Thanks, everybody.